Alrighty, welcome back everybody. So now that we know how to do integration to find the area between two curves, that makes a great segue to learning how to integrate with respect to y instead of to x, which is what we've standardly done. So let's go ahead and look at a typical problem that we've seen before. So let's have f of x be equal to x plus 6 over 5. So that's just, it's kind of written in a funky way. You'll see why I did that in a minute, but that's just a straight line, right? Slope is 1/5, y-intercept is 6/5. And let's compare that with the function g of x, which will just be the square root of x. So that's just the upper portion of a sideways parabola. And let's go ahead and graph that on the calculator. So I'm just going to pull that up right here. Now, unfortunately, when we do it, it's kind of squishy. It's a little bit hard to see when it's actually drawn to scale. But this is the area we want. I'll just go ahead and highlight that in yellow. So the first order of business is to figure out what our bounds of integration are going to be. So we need to find these intersection points. And we do this just by setting our two equations equal to each other to find the x that makes these two y coordinates the same. So we go ahead and set them equal to each other. And I don't like fractions, so I'm just going to go ahead and multiply that 5 over. Don't like radicals, so I'm going to square everything. This one's a perfect square trinomial. Notice when you square this, 5 becomes a 25. Radical x1 squared becomes x. One thing I should point out is x here is positive. So, yep, we scoot the 25 over. Everything factors nicely, and we get that x could be 9 or x could be 4 in terms of where the intersections are. So I'm just going to go ahead and put that on there. So that intersection is 4, that intersection is 9, and it's not going to be you don't have to do this next part, but I'm actually going to figure out the y coordinates, and it turns out that's going to be useful anyway. And actually, it's not completely irrelevant, because how would we know if we didn't see the graph right here that maybe one of these answers might be extraneous? Remember, that's always a possibility when you're solving a radical equation and squaring things, that you might have introduced solutions that don't match in the original. Oh, excuse me. I'll have to edit that out in the final. So let's go ahead and actually plug the x back into each of these and see that it comes out. So when x is 4, this equation right here would be 4 plus 6, which is 10, divided by 5 is 2. On the other hand, the g of 4 is square root of 4, which is 2. So in fact, that's just going to be 2 there. And what about this y coordinate? Let's verify that it's the same y coordinate whether we plug it into red or blue here. So when we do f of 9, 9 plus 6 is 15. 15 divided by 5 is 3. On the other hand, when we plug it into the red parabola here, we get the square root of 9. Oh, that's also 3. It might be worth noting here, square root of 9 is not plus or minus 3. It's only plus 3. The radical symbol means only give the positive version. So, all right, so there's the 3. It's worth noting that these y coordinates actually don't directly come into play for future calculations right now, but it might be important for checking our work later on, which you'll see. So, all right, at this stage we're actually ready for the integration, and we're going to integrate as we normally do, which is called with respect to x. That means our variable is going to be x, so we're chopping up the x-axis. So essentially we're looking at these little vertical segments here. We put them on there. There's our little vertical segments. So when we do our integral, it's going to be the integral from 4 to 9 of the top function, or it's the thing with the higher y values, take away the bottom function, the thing with the lower y values. So here we can see between 4 and 9, the red probably thing is always on top. So it's going to be x to the 1/2, that's the square root of x, I just wrote it with exponents, take away the blue line, which is x plus 6 over 5. And again, this is all with respect to x, so the dx there. And now we just integrate each of these little bits using the power rule. So the integral of x to the 1/2 is 2/3 x to the 3/2. And I'm just going to split this up. So we have minus x over 5 minus 6 over 5. So when I integrate it, it's add 1, divide by the new exponent. So the 1 becomes a 2, and then the 1/5 becomes a 1/10 divided by 2. And last but not least, we got the minus 6/5 when we integrate it is minus 6/5 x. We're evaluating it between 4 and 9. And at this stage, it's just plugging into the calculator. I mean, it's not even that bad to do it by hand, because you could do 9 to the 3/2. Remember, the 2 here at the bottom of the exponent here means square root, so square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9. 2 times 9 is 18. And you just keep on doing all that. And you get negative 9/10. Take away a minus 16/15 is 1/6. Okay, so it's doable, really wasn't that tricky. A little craziness with fractional exponents, but we get the answer is 1/6. It's worth pointing out that this number had to be positive. If we ever get a negative area in a region of a plane, we probably did something wrong. Alright, so far this is all stuff you know how to do. Now let's go on to the new way of looking at it. So I'm going to redraw it, and rather than doing the calculator screenshot, I kind of want to exaggerate the features. So there's our square root of x. There's our line, x plus 6 over 5. And here's the area that we're going to be looking at. And I'm going to go ahead and put on our intersection points. But this time we're going to do something a little bit differently. So rather than chopping things up with vertical lines and integrating with respect to x, we're going to imagine chopping things up this way. We're going to look at it from the y-axis point of view. So now if that confuses you, you can just tilt your head to the right and kind of pretend like, all right, this blue line's on top and this parabola curve here is on the bottom. But we're just going to write it in terms of y's. So this is the way we're going to be slicing up. We're essentially adding up these lengths. So everything is now going to be a function of y. So before, we had y, everything was formulas of x's. Y equals a formula of x's. Our bounds were in x's. Everything was x's. This time, everything's going to be with y's. So the first thing we need to do is get our bounds of integration right here. We can imagine these rectangles going this way instead of this way like they normally do. So we need to figure out what these tick marks are. Well, we already know they were 2 and 3 because we figured out before on the other page. But let's go ahead and do this from scratch. So what you're going to want to do when you get it with respect to y is rewrite everything with y. So instead of y equals a formula of x's, it's going to be x equals a formula of y's. So instead of y equals x plus 6 over 5, we just rewrite that by multiplying both sides by 5. So you get that 5y equals x plus 6. And then subtract the 6 over. So 5y minus 6 is equal to x. So that right there is our blue line. And then we just do the same thing with our red curve. So y equals square root of x, so x is y squared. So now, again, to find the intersection points, we want the y's. So we get the y formula is equal to, the x formula is equal to each other. So we set these y equations like that. And notice this time it's a little bit easier. The algebra is actually easier. I mean, you just see it on the screen just plopping right there. But when you actually work it out, I mean, before we had to like square both sides and then check for extraneous solutions. Here it's just a regular quadratic equation. Y squared equals 5y minus 6. Scoot everything over to this side. Y squared minus 5y plus 6 equals 0. Factors beautifully. Y equals 3 or y equals 2. So of course, we already knew it was 2 and 3, but now we have official confirmation writing it in terms of y's. All right, so now we're ready to set up our integral. So this time the integral is going to go between 2 and 3. And before, we always did the top minus the bottom. This time it's going to be the function that's on the right take away the function that's on the left. Now that might seem kind of arbitrary, but if you think about it, it makes sense. Tilt your head, and this is the one that's on top. Right? You have to tilt your head to the right. So technically, you're saying this is the higher value subtracting the lower value, because we always want these lengths to be positive. So in this case, so notice before when we do it with respect to x, it was the red curve minus the blue line. This time it's the other way around, right? So this time when you tilt your head, the blue is on top and the red's going to be on the bottom. So we're going to do right minus left. So the line, which in this case, remember, we're writing in terms of y's. So the line is 5y minus 6. You can think of that as giving you the x-coordinate of this whole thing. And then we have to subtract off the x-coordinate of the red line. So we have to subtract off y squared, right? So blue equation minus red equation. And again, this time it's all dy. We're chopping up the y's. This is all with respect to y's. There's no x's in this. So, and notice, again, this integral is a lot simpler. There's no square roots. There's no fractional exponents. It's just a straightforward integral. So 5 halves y squared minus 6y minus 1/3 y cubed. We're evaluating that between 2 and 3. Number's a little smaller, so a little side benefit there. Anyway, you plug it in, and lo and behold, you get 1/6. So notice you get the same answer as before. That's a good thing, right? Because this is the same area, right? This is the exact same graph, right? So it doesn't matter whether we say y equals x plus 6 over 5 and look at the y as being a function of x, or whether we look at it as x equals 5y minus 6 and think of the x as a function of y. it's still this line. It's still the same area. So thankfully, our face in math is justified, and both answers come out to be the same.